Hey guys, so I am recording this lecture for you because we missed a couple lectures. Usually I do miss a few here and there, but I didn't intend. All of them seem to have stacked up right next to each other this semester. So what I was planning to do is to have a few recorded lectures for you guys, but to do them slightly out of sequence. For example, this is for a lecture for slide deck 5. Our next live lecture, we're going to cover slide deck 4, but this will give you a chance. Like, you could either look at this before that slide deck 4 or afterwards. Either way it'll work. That way I was hoping like you wouldn't get scrunched for time where I'm asking you guys to go through 2 or 3 lectures in a row, and miss some concepts during the live. So hopefully this will work. So anyway, you might have already seen or attended lecture 4 before this, or the lecture for slide deck 4, or not. Either way, it's kind of it's okay if it's in out of sequence somewhat. This slide deck talks about the MOS transistor, which is the sort of the basic unit for all chips, that almost all the chips that we have today. And hopefully it's a review of stuff you've seen before. Again, the MOS transistor. But this is just in case you need a refresher. We all do. I do all the time. I'm going to go through and talk about, basically derive the MOS and NMOS characteristics for both the NMOS and the PMOS, starting from a MOS capacitor idea. And then we'll talk about some of the details of the capacitance and so on. So, just sort of as some background reminders, or just some background thoughts, again, from, I think we might have already talked about this somewhat, but, I'm sure maybe or seen it in lecture 4, etc. But let's cover it a bit. So, there's different degrees of, we move on different degrees of sophistication of looking at a particular device, the transistor being a particularly good example in this class. So, we can look at it as a really simple switch. So, we talked about doing the reason that, transistors are good, useful, is because of, that binary math is particularly efficient and good. And so we need basically these transistors to make gates. So the transistors, let's say a MOS transistor, makes a gate. Let's say I'm going to do a NAND. It turns out that NANDs are particularly efficient in the CMOS logic family. And then the gate does some binary math depending on its inputs and outs. Say A, B. How does this go? Let's see. So AND would be 1 here. So this would be 0, 1, 1, and that's the output. Okay, so this is kind of what we want to basically, this is what we'd like, basically doing a mathematical binary math operation or binary logic operation. And then, so to have this, the physical thing, the imaginary physical thing we'd like to make is a gate. And how do we make the gate? Well, the sort of a particular useful device is a transistor. So as we'll see, or maybe you guys have seen again, like what we really would love to have is just a switch to make the gate. We'd like to have like a perfect switch that has, that has a control. Let's say, this is, I don't know, I'll call them for this minute, out. Let's see, out. Let's call this in and call this control. Those are just sort of random names I'm making up here. So ideally, in a perfect situation, you're just like a perfect switch. You have a control that either connects these nodes together or disconnects them, and like with this, you basically design your gate. But we don't have this, unfortunately. We don't have an ideal switch, and we're using these transistors to emulate this switch. To make a switch, it makes a pretty good switch under some circumstances, but it's not an ideal switch. So that's what the stuff we're going to talk about today is why, how does it actually work? And then we'll talk about how that causes sort of certain non-idealities in a switch. So to start with, I'm going to sort of give you guys the punchline and then walk through it. How does this, what kind of switch is a NMOS transistor? So NMOS transistor, the schematic symbol is this. The PMOS transistor looks awfully similar, except it's got a little bubble on the gate. And then it turns out the nodes are gate, drain, source, and then the gate, drain, source for the PMOS. And so the gate is typically in a logic sort of use for this device. Gate is the controlling element, and you're trying to use the device like a switch like this. So the gate is the control, and then you're trying to pass stuff from the source to the drain or vice versa, depending on how you want to look at it. So you could think of the drain as being the out and the source being the in, or vice versa. Basically, you're just trying to connect these two nodes. If in the case of an NMOS, again, from a really simple theoretical, or not from an ideal standpoint, if the gate is a 1, say a logic 1, sometimes I'll call it a logic 1, sometimes I'll call it high, like a high value, and sometimes I'll give it a voltage. So it'll be, one in this class, mostly we'll talk about 1.8 volts, but it's the highest voltage in the chip typically, or in that for those transistors. So I might also call them VDD because that's the highest logic for the transistors. And these are all like actually the same thing. It's just different ways of looking at the same thing. So in actuality, we're putting in a voltage, whether it's this VDD for different processes could be, might be 1.8 volts, it might be, 1.2 volts, it might be 0.9 volt. So there's a bunch of options there. And then depending on what those are, this will be the actual voltages that go on the gate. But the concept of high and 1 are just always the same. They're sort of like you're saying that my VDD value in this particular process is a 1, is a binary or digital 1, okay? So for a NMOS transistor, if the gate is high, if the gate is high, sorry, let me first say this, I'm still simplifying. So if the gate is high, so gate is, let me just call it 1. Gate is a 1. It's going to connect the drain and the source together. Okay, and if the gate is a 0, it's going to not connect those two together. So the switch will be on if the gate is a 1. Okay, so now what is a gate equal to 0? So a gate equal to 0, these are all equivalent. You can hear it being a low, a logic low, or it's 0 volts, and it's always 0 volts. So this one, because of the way CMOS processes work, your 0 is always, your 0 or low logic value is always 0 volts. And then your 1 is the highest logic, the highest voltage you have in that for that particular transistor, which could be again 1.8 volts, 1.2 volts, 0.9 volts. A lot of times we'll see 1.8 volts or in the labs and so stuff we do in the class, but it could be 1 volt or 1. It depends on the process. Okay, so now so a logic 0, a gate value of 0 on an NMOS means that there's no connection between drain and source. So the PMOS is somewhat like the opposite. So it is for a gate value of 1 on the PMOS, you have an open switch between drain and source. And for a gate value of 0, you have a closed switch. So in some ways, and this is why it's called the CMOS logic, CMOS. CMOS stands for complementary MOS process. And this complementary, the reason the complementary is because in some sense PMOS is complementing the NMOS. Or the two devices are complementing each other. One of them is on when the gate is high and vice versa. Okay, so that's why it's called a complementary MOS process. So that's the basics. Now, one additional thing, again, hopefully we'll talk about this. You would have seen this before, or we'll see it plenty of times later. The real device, or the next level of complexity. But let me actually start a new page here. So this is let's call this level 0 of model of this thing. Just plain old gate is high, you connect these two nodes, gate is low, you disconnect them in a PMOS, and vice versa here. So gate is 0, you connect drain and source, gate is 1, you disconnect drain and source. So that's sort of your level, whatever, baseline model. Okay, so the next level of complexity is that it turns out, and this is very important, it turns out that an NMOS is good at passing a 0 from source to drain, but not good at passing a 1 from source to drain. Okay, so the actual value that you're trying to pass, whether you're trying to pass a 0, when this guy's on, okay, when it's off, it's off. When the gate turns the device on, if you're trying to pass a 0 from source to drain, it does a great job. It exactly passes the 0 from source to drain, which notice again, these are different levels of abstraction. When we are talking about ones and zeros, we are in the logic domain or binary domain, this sort of imaginary. It's actually not, the real device doesn't work that way, but we'd like a 0 or a 1 to go perfectly from source to drain. That's the only model we have in a logic, sort of in a logic abstraction, but it doesn't do a good job of that, of putting a 1 from source to drain. And what does it mean that not good means? It sends a, what does meaning non-good mean? Not good means that we have a degraded 1. Somehow this 1 is not as good, it's not as useful, it's like a dangerous 1 in the sense that it might have lower noise margin, it might have lower drive strength, etc., and we'll see that in detail. So somehow that 1 isn't as good. You still get a 1 here, depending on if you're clever enough, if I define zeros and ones, but it's not, it's a kind of it's not as good as a real one. You'd like a really clean one. Imagine in a binary function or in your computer or your chip, you're doing, God, I don't even know what you're doing billions and billions of logic operations a second, right? You're doing lots and lots of operations a second. So there's lots of opportunities for things to go wrong if you do not have the more you deviate from a perfect binary situation. Perfect binary situation would be perfect zeros, perfect ones, everything is sort of just, there's no currents or voltages, there's just zeros and ones, and there's no noise that would make you get confused, a one with a zero or zero with a one. But all those things in reality are there. And the problem is you're doing lots and lots of operations every second. And if any of those operations are wrong, typically you are somehow hosed. Okay, you're either gonna have an incorrect answer, or maybe the chip is gonna get hung up. Something bad's gonna happen. Anyway, so degraded is just like a dangerous situation and not good, and you want to do something about that, make it better. You don't want a degraded one. Sometimes you might live with it, but you really don't want to have it. Okay, so PMOS is good, is again, in some ways, the two devices are complements of each other, also in the sense that PMOS is good at passing a 1 from source to drain, but not good at passing a 0 from source to drain. So for a PMOS, again, this is like not good, means that you get degraded 0. Let's talk a little bit about what a degraded means. Degraded, okay? So now, this is from a binary standpoint. Now let's think about it in terms of the voltage standpoint. So from a voltage standpoint, I said, a 0 is, a logic 0 is always 0 volts. And the logic 1 is the supply voltage. For the sake of this discussion, let's say it's 1.8 volts. Okay, so that's our logic 1. So a degraded one may mean that instead of 1.8 volts, you might have 1.2 volts at your drain. So instead of if you had 1.8 volts here, instead of getting 1.8 volts here like you would really like, because that's your real definition of a good logic 1, you might only get 1.2 volts here. And that, as we'll see, sort of starts causing problems. And then a degraded 0, so may mean that instead of 0 volts at drain, you might get 0.7 volts at drain. So again, it might be 0.7, it might be 0.5, but it's not 0. It's something other than 0. It's looking kind of like a 0.7 volts, if you're calling that a 0, if you think of it as somehow like this, again, binary logic. A 0.7 volt value is starting to get closer to a 1.8 value, closer to a 1 than a 0 is. So if you have a noise or anything like that, something disturbs the system, it's easier to confuse 0.7 volts for 1.8 volts than it is 0. So you'll have much lower noise margins. We'll see what that means with a degraded 0 than a a normal 0. Okay, so that's the next level, is these guys, these transistors are not good at passing either a 1 or a 0, depending on the transistor type. Okay, so the next thing, and I'm start talking about the sort of the main crux of our class, is that the real model of a transistor, again, this is what we're gonna talk about in this class, and then sort of see how this relates, how do you use this as a switch, is quite different than either one of these. I mean, well, I guess it is different. Okay, so that's not, I don't know if quite different is the right word, but well, okay, it is quite different. Okay, so we're gonna have to like do some creative work to make it look, make a transistor look like any of these switches. Okay, so an NMOS transistor. So transistors, if you guys remember, are, so now I'm not going to talk about binary, I'm not going to talk logic, we're going to talk about voltages and currents. So now we're in transistor land, we're going to get into the nitty gritty, and then, then try to figure out how to get from here, voltages and currents, to any of these switch models. Okay, so NMOS, and then we'll talk about this in the slides. Because it's a 3-terminal device, so we have 3 terminals, gate, drain, source, we need 2 graphs to show how it works, because you can, let's say you have, we call the voltage at the gate VG, we call the voltage at the source VS, and the voltage at the drain VD. We can hook this up in this device into 2 ways. We can have, let's say we just hook up the device in 1 way, but we sweep things in 2 ways. So let's say I have 2 voltage sources. So this is VGS. So this is between, the reason it's called VGS is between the gate and the source voltage. So here, let's assume the source is always a ground. And then VDS, which is between the drain and the source. So I can do one of 2 things, because I have these 2 guys, and I want to measure the current, IDS. So that's the current that goes from the drain to source. Okay, so either I can hold VGS constant and sweep VDS, or I can hold VDS constant and sweep VGS. Okay, so that's why there's 2 graphs that define, we normally look at 2 graphs for each of the transistors, NMOS or PMOS. So the first one is drain source voltage versus IDS. Okay, so in this case, we are holding VGS constant and then sweeping VDS. Okay, so let's say for the sake of discussion, this is like only for a illustrative purposes. I mean, these voltages I'm going to talk about are kind of, I'm like kind of making some stuff up. Okay, so let's say you have VGS, you're going to sweep from 0 to 1.8 volts. Okay, and then let's say we start with a value of VGS is equal to, start with VGS is equal to 1 volt for whatever reason. Okay, so in that case we might get a curve like this. So this is a curve of the drain source current versus VDS at a VGS of 1 volt. So here, you at 0 VDS value, when this difference is 0, you basically get 0 current flowing. And as you increase the VDS for a while, okay, for a while it looks kind of like a resistive function. So remember a resistor, so a resistor as a transfer function, whoops, as a transfer function, something like this, with this being 1 over r. I mean, this should have been, sorry, should be a straight line, not a wiggly line. Doing a really bad job here. Okay, so resistor should look like a straight line with 1 over r. So, you know, if you kind of close your, you know, slightly squint your eyes and in focus, you know, a foot behind, like 6 inches behind the screen or whatever, this might look like a resistor, right? There's kind of this line. It's pretty non-linear, but it kind of looks like, maybe it's like kind of a crappy resistor, a non-linear resistor up here. Over here, it doesn't even, as this, you know, to our first model, almost looks like a flat line, meaning that as you change VDS, once you get past a certain point, as you change VDS, the current isn't even changing. And so you don't even have anything that looks like a resistor here. This looks more like so here, it kind of looks like a non-linear resistor, let's say, or crappy resistor, I don't know what I'm gonna call it. And here, it looks like the device looks like a current source. So a current source is, you know, if you think of a current source's IV characteristics. So a current source is just, no matter what you do, a current source, no matter what voltage you put across a current source, the definition of a current source is it always pulls the same current. So if you look at the IV curve of a current source, no matter what this voltage does, the current is always constant. So here it looks like a current source. And I'm throwing a lot of stuff at you guys, again, hoping you've seen this before. If not, we're gonna go in detail and look at this. And then if you have, so this was at holding VGS constant at 1 volt, say. And if you say did VGS is equal to 1.8 volts, you'd get sort of a similar curve, but it would move. It would maybe do something like this. So this would be for VGS is equal to 1.8 volts. So it would still have this region that looks kind of like a nonlinear resistor, and a region that looks like a current source, and also the values of the currents are higher than they were in the VGS equal to 1 volt. And then if you reduce the voltages, reduce VGS, let's say to, you know, let's call it VGS is equal to 0.8 volts, say, you might get something like this. So again, you have a linear period, and then a straight line after that. The locations change, and the max current changes. Notice this is the current line. So, but you know, just sort of these curves of different VGSs. Okay, and then if I'm just holding, the other way I can do this is to hold VDS constant, so for various values of VDS, and I can sweep VGS, and it turns out that actually, so if I get VGS versus IDS, I'll get, sort of theoretically, I'll get a bunch of curves. They should kind of sit on top of each other, but they really don't. I mean, for different VDSs, I'll sort of get like different values. And they should all take off at the same place, from a place called the threshold voltage that we'll call V sub t. So this is the threshold voltage. But in fact, this V sub t is dependent on VDS as well. So it gets like even to the second and third order effects here. Okay, so that's where we're gonna get to. I drew the NMOS for you guys. The PMOS is sort of, everything is somewhat inverted from this, and we'll see that. But anyway, I'll keep going from here, but you know, you can just sort of look it up. Oh, well, we'll see it later too. So anyway, so So, okay, so now, sorry, after all that, we're really just at the introduction, unfortunately. So this might take a few different lectures, but hopefully the details aren't boring you guys and sort of actually adding some value here. So again, this is saying what I've been saying so far is that, you know, there's the ideal and then semi-ideal model of a transistor as a switch. But then, you know, when you're talking about an actual transistor, you have, you know, different current versus voltage characteristics like we talked about here. And then, you know, towards the end of the lecture, we'll also see how there's different capacitances that affect the speed and so on. So this may be a good segue also to talk about this. Okay, so we want to pass a value of a 0 or a 1. So we don't want a this is all talking about voltages, right? So we've been talking about a voltage of 1.8 volts for a 1, or for a 0, we have a voltage of 0, say, okay? That's 1.8 could be different. It could be 1.2, 1 volt, whatever, but 0 remains 0. Okay, so far we've been talking about voltages, and ideally you'd like to keep these values, right? To get a good, we said, you know, you don't want a degraded 1 or a degraded 0, but you want to keep these values as it is. So, okay, great. So, but that's just talking about voltages, but somehow current, as you would guess, is going to come into this as well. And so how does the current come into this? Like if you could pass a 1.8 volts with, you know, let's say if you think of a resistor with, you know, it's 1.8 volts here and 0. This could be, you know, I don't know, let's think of this could be a mega ohm. So 1 times 10 to the 6 ohm. And to establish this no, I'm going to confuse you guys with this stuff. Forget about this. But let's say if you're passing depending on the resistance of the transistor, if you're passing a 1.8, you could either do it with very low current or with very high current. So does the current matter? And the answer is yes, the current matters, but the current matters to the speed of operations of the device. To get a good or a non-degraded 1 or 0 means you have a reliable logical operation. But the question is, like, at what speed? Like, how fast can you switch your 1s and 0s? And that's where the current comes in. So the higher the current, so it turns out that what we're doing in these gates is we are charging using these switches. So PMOS, say, we're stacking these up, so an NMOS. So what we're doing is we are charging and discharging capacitors. And the capacitors are really, these capacitors are really the gates, of the next logic gate you're driving. So you got to charge and discharge the next logic gate. So, and the speed at which you charge and discharge a capacitor is dependent on the amount of current you have to charge or discharge. Okay, because, and the basic equation of that is if you have Q is equal to CV, okay, so charge is equal to capacitance times voltage. So if you look at the current, which is dq dt, take the derivative of both sides. So if you want to see how fast you can charge and discharge that node, this dV dt, that's equal to I over C. Okay, so the higher the current that you have, the faster this change in voltage with time. So the faster you can transition from a 1 to a 0 and vice versa. And the higher the capacitance is, the higher the load that you're driving, the slower this will be. Okay, so this combination of your current drive